Electromagnetic compatibility issues can sneak into your design in the most unexpected ways, and your cables may be radiating more noise than the circuit itself. The distinction between common mode and differential mode noise is critical for identifying potential sources of radiated emissions. In this video, we'll explore why these two modes behave differently when it comes to radiated emissions, and identify which one may cause the bigger problems. The first test setup consists of two DC lizens based on a typical CISPR25 test configuration. These lizens are connected to a TechBox LisenMate, which allows for separate measurement of differential and common mode noise. On the input side, the lizens are connected directly to the reference ground plane using low impedance connections. On the equipment under test side, the lizens are connected to a standard 2-conductor power cable, which in turn connects to a broadband noise source through a 3 dB attenuator. The noise source used is a TechBox TBC G4 harmonic comb generator, which produces a flat comb spectrum up to 1 GHz. For the first test, the center pin of the SMA connector is connected to the red wire, while the ground side is connected to the black wire. This configuration primarily generates differential mode noise, where the signal travels in opposite directions on the two wires. The differential nature of the signal is confirmed using the TechBox LisenMate. Its differential mode output is connected to channel 1 of the oscilloscope and the common mode output to channel 2. The oscilloscope clearly indicates that differential mode is dominant in this setup. A negligible amount of unintended common mode noise is also present due to asymmetry in the test configuration. When the wires are probed with a magnetic field probe, very little emission is detected. This is because the opposing magnetic fields from the two conductors largely cancel each other out. Complete cancellation would only occur if the conductors were infinitely close. Since they are separated by a finite distance, only partial attenuation occurs due to destructive field interference. It is also notable how the magnetic field probe's position between the conductors affects the detected signal. The amplitude is highest near either the red or black wire and lowest when the probe is positioned equidistant between them. Additionally, the polarity of the detected pulses changes, positive near the red wire and negative near the black wire. The negative pulses are also visibly smaller than the positive ones. This asymmetry introduces residual common mode noise, primarily caused by a secondary ground path from the comb generator through the USB power cable to the oscilloscope. Consequently, probing the USB cable reveals these negative pulses. The radiated emission characteristics change significantly when the setup is modified to promote common mode propagation. In the second configuration, a resistive splitter is used to divide the output of the comb generator equally between the two wires. To compensate for the splitter's internal 3 dB loss, the previously used 3 dB attenuator is removed. The ground side of the splitter's output is connected to the reference ground plane. A quick verification using the LisenMate and oscilloscope confirms that common mode noise is now dominant. Probing the wires again with a magnetic field probe reveals significantly stronger emissions. What the? Since the signals now travel in the same direction along both wires, their magnetic fields no longer cancel, but instead combine constructively, increasing the observed field strength. If the conductors were infinitely close, they would act as a single entity, and the field lines would resemble those of a microstrip line as shown here. However, the electric field lines would curve less due to the lower relative permittivity of the insulating material. Since the difference is admittedly hard to spot on the oscilloscope screen, not only but also because of the limited bandwidth of the oscilloscope, I repeated the test setup using a fixed position of the magnetic field probe, a spectrum analyzer, and the software EMC view. This is not a standardized test setup, and the measurements should only be considered for relative comparison. After performing this measurement both for the differential and common mode, here are the results. The frequency sweep ranges from 30 MHz to 1 GHz, with both average and peak values displayed. A combined plot of peak differential and common mode measurements clearly shows that the common mode signals produce stronger magnetic fields. The difference would be significantly greater were it not for the aforementioned asymmetry caused by the USB connection. Until this point, measurements have focused solely on the near field. Due to the chaotic and complex nature of near field behavior, a non-standard far field measurement of the electric field strength is also performed. For this purpose, a calibrated biconical antenna, the TechBox TBMA-1B, is used. This antenna provides well-defined antenna factors between 30 MHz and 3 GHz, allowing for accurate field strength measurements of radiated emissions. Although the improvised setup limits absolute accuracy, it remains suitable for relative comparisons between common mode and differential mode signals. The antenna is positioned 50 cm from the two-conductor cable. As a rule of thumb, the far field distance is given by the wavelength divided by 2π. Rewriting this in terms of frequency and inserting the 50 cm distance shows that the antenna is in the far field zone for frequencies above approximately 95 MHz. Using this setup, the radiated emission spectrum is measured again from 30 MHz to 1 GHz with a CISPR-compliant resolution bandwidth of 120 kHz. Measurements are performed twice, once with differential mode excitation and once with common mode. The combined peak results closely mirror those from the magnetic field probe measurements. Despite some asymmetry in the test setup, introducing common mode components into the differential configuration, the experiments clearly demonstrate the more radiative nature of common mode noise. This video lays important groundwork for upcoming content on radiated emission issues. If you were hoping for more in-depth coverage of standard compliant field strength measurements, don't worry, that's coming soon. Be sure to subscribe and turn on notifications so you don't miss it. While I'm committed to providing educational content free and accessible to everyone, channel members get early access to new videos. If you'd like to support the channel and help keeping content coming regularly, consider becoming a member. See you next time.